All right, let's talk about a huge misunderstanding when it comes to large language models. Seriously, it's something that causes massive problems for anyone trying to build a reliable AI system. We're going to dive into the hidden cost of language.
Okay, so let's just start with the most basic question you could ask, right? How do these incredibly powerful models actually read and understand the prompts we give them? I mean, we talk to them in plain English and they seem to get it. But how does that actually work under the hood?
Well, the simple and honestly kind of shocking answer is they don't. Not in any way that you or I would call reading or understanding language. And that one simple fact, it's the root cause of countless bugs, insane budget overruns, and system failures that just leave you scratching your head.
So let's peel back that illusion and get right to the engineering reality. Because if you want to build robust applications, you have to stop thinking like a user and start thinking exactly like the machine does. Here is the first thing you absolutely have to get. Before a large language model ever even sees your prompt, there's this other thing, a separate non-AI component called a tokenizer that gets its hands on it first. And for the machine, your language is just a stream of numbers, a sequence of integer IDs. That's it. And this whole process, it isn't free, not by a long shot. Every single piece of text you send to a model comes with a cost, a tax. And for the rest of this explainer, we're going to call it the token tax. So let's take a super simple, everyday request you might build into a customer service bot for an airline. Refund ticket hashtag UA92. To you and me, that's a clear 5-word instruction, but that is not what the machine sees at all. Okay, this visual right here explains everything perfectly. Up top, you've got the user's view. Refund ticket hashtag UA92. That text gets fed into the tokenizer, which you can just think of it like a paper shredder. It doesn't care about your words or your grammar. It only cares about common strings of characters that it's seen a million times before. Now look at the output, the machine's view. Refund becomes token 482. Ticket is 111, but look closer. The pound sign, UA, and 92 are all shredded into their own separate tokens. Every single one of these little integer chips has a real dollar cost, and it takes up precious, finite space in the model's memory. And that is the crucial point here. Tokens are the fundamental unit for everything an LLM does. They are the unit of billing you literally pay per token, they're the unit of memory every token you send eats up a slot in your context window, and they're the unit of speed. The more tokens you send, the slower the response is going to be. And remember, all of this is decided by that simple, non-AI preprocessor. So once you really understand this token-based reality, it immediately exposes 3 hidden constraints that, honestly, every single engineer needs to burn into their brain. And these aren't just theory, they have direct, painful, practical consequences on your app's performance and its reliability. Okay, so constraint number 1 is what I call math blindness. This is why models can seem so bizarrely bad at simple tasks, like just reversing a number. For a common number like 392, the tokenizer might just map that whole thing to a single token, let's say ID 4421. The model never sees the individual digits 3, 9, and 2. It just sees one abstract concept. It can't read the digits to reverse them. It would have had to memorize the reverse sequence as a totally separate fact. Let's talk about constraint number 2. You see these big, flashy numbers advertised for the latest models, 128,000 tokens. That's the model's context window, which is basically its entire short-term memory. And let me be clear, this is not a suggestion. It is a hard buffer limit. The second you send token number 128,001, the oldest information, the very beginning of your conversation, the top of the document you sent it, is just deleted, truncated. Poof, gone forever. The model has absolutely no memory that it ever existed. And now for constraint number 3, the one we all feel, the very real dollar cost. Your build per 1,000 tokens, which works out to be about 750 words. So the more verbose your prompts are, the more you pay. It's that simple. And for user experience, this is critical. Your input tokens are the number 1 driver of latency. So huge prompts mean slow, laggy applications. Okay, theory's one thing. Let's see how this plays out in a real-world scenario. Imagine a junior engineer at a fictional airline. Let's call it SkyStream. They're building a tool to look up passenger name records, PNRs, and they make a fatal mistake. They assume the PNR is just simple text. So an agent enters the PNR, XJ92KP. Now, because this is just a random-looking string of characters, the tokenizer has no idea what to do with it, so it just breaks it up into little pieces it recognizes. Maybe it sees XJ, then 9, then 2, then KP. Suddenly, the model is seeing 4 distinct tokens, not one single unique ID. This makes it way more likely to hallucinate or forget one of the middle pieces, and it makes doing an exact match search in a database basically impossible. The whole system just fails. This same lack of token awareness leads to another massive cost trap. Let's call this one the verbose policy mistake. You want your AI agent to know the company's baggage policy, right? Well, the naive, easy approach is just to give it the whole document.
But think about this. If you paste that entire 10,000-word PDF into the system prompt for every single user query, you are paying that token tax over and over and over again. You could literally be spending 10 cents for every question asked just to have the model reread the same static document it literally just saw 2 seconds ago. It is an incredible waste of money and time.
So what's the better way? The bad pattern is obvious now, right? Pasting the whole document every time. The production-grade pattern is way smarter. It uses techniques like retrieval augmented generation, or RAG. All that means is you search the document first for the relevant bit of information, and then you inject only that one single relevant paragraph into the prompt. It's targeted, it's efficient, and it is dramatically cheaper.
So, we'll just leave you with this question. Now that you've stopped seeing language as words and started seeing it as a sequence of costly memory-eating integers, how does that change the way you're going to architect your next prompt, or your next feature, or your next AI application? Because that difference in thinking is what separates a fragile demo from a scalable, production-ready system.